of GSI. So on behalf of the organizing committee, it's our great honor and pleasure to welcome Professor Giovanni Pistone from Collegio Carlo Alberto in Italy. His talk will depart a bit from most of the talks that consider parametric models, and he will address a key issue on non-parametric information geometry.
Bonjour, c'est un plaisir pour moi d'être ici. J'ai étudié en France, j'ai fait le 3e cycle à Rennes, et je voudrais dédier mon talk en français, je voulais, à mon maître à Rennes, professeur Michel Lequivier. Good morning. I'm going to talk about non-parametric information geometry, and actually on the slide you see the link to this presentation. During my talk, I am using quite freely, without quotation, work of many other people, most of them in this conference, but I'm not giving during the presentation detailed reference. You can find the reference, almost all the reference, in the paper in the proceeding, and in another paper where I have developed one of the example, precisely the example concerning the treatment of Boltzmann entropy and Boltzmann equation. And unfortunately, there is a big number of, large number of typos in the paper in the proceedings, and some of them are corrected in a version of the archive. I am going to, in some sense, I am going to follow quite closely the presentation by Professor Amari yesterday. And in particular, going back to his slide on the history of information geometry, I would like to recall two important contributions from my point of view. One is a contribution by Efron, and the corresponding comment by Phil David, and the other one are the contribution by Professor Amari and Professor Nagaoka. These contributions are important because with the paper, at least for me, with the paper from by Efron, there was a sort of switch of paradigm, moving from the focus on Fisher information and the related Riemannian structure to actually a different geometry, a geometry based on exponential families. So Efron ideas is to take a statistical model and put it in a larger exponential family, and then use the structure of the exponential family to discuss the statistical model. So actually this means that there are at least two geometries on the probability space, the geometry induced by the exponential structure and the geometry induced by the Fisher information. And actually, the great contribution by Amari and Nagaoka to explain that there is a full family of geometries, and the most important being the geometry of the exponential family, this geometry has a dual counterpart, which is just the geometry of the simplex, and in the middle there is the Riemannian geometry. So anyway, my point of view is the point of view of Ephron in some sense. So first remark is that there is a basic invariance in statistics, and is the fact that the same in statistics they teach that it's not the probability which is important, it's the likelihood. And two different statistical models can be represented by different likelihood with respect to different reference measures, but the inference should be the same. And a valid option is to consider the Fisher score, which is independent. The Fisher score being the derivative along the model of the logarithm of the likelihood. So the Fisher score does not depend on the reference measure and has expected value 0. And now the next point is find the largest possible exponential family where I want to embed my specific model. Now every density Q, which is equivalent to a given density P, is of course of exponential form, because every positive function is an exponential of something. And the random variable that appears in the exponent, here denoted by V, has to be, is not a generic random variable, because the exponent, the exponential function of V has to be integrable. So this is a basic and avoidable condition. But to avoid, for technical reason if you want, or for more basic reasons having to do to the fact we want to avoid the situation where we are near the border of our structure, we actually require a bit more. That is to say that the expected value of the e to the power theta v is integrable for all theta in some open interval, which is in some sense the same as requiring the existence of the one-dimensional exponential family. So, my plan, as you see, is the same as the plan of the Professor Amari talk. I talk about exponential family, then I talk about vector bundles, or if you want, connections, and then I talk about some more recent development called deformed exponential families. So my point is that I don't understand at all the parametric version of differential geometry. So for me, I must confess that gamma ijk, I don't understand what does it mean. So my version does not have any of this notation. It's purely functional. So, first of all, we have to distinguish a number of sets of probabilities. We have the set of strictly positive probability, which is the usual ingredient of statistical models. We have the set of not probabilities, more precisely I consider densities. We have the set of densities. Unfortunately, the set of densities is not suitable for constructing an infinite dimensional geometry, because the positivity condition is not a topological condition. the set of strictly positive integrable functions is not an open set in L1. So there is a contradiction between the positivity and the topology. So in some cases we are forced to go to a bigger space, I call it P sub 1, which are functions without any restriction on the positivity, but with integral equal 1. So I want to define a differential geometry on this space, which in a way which is meant to be a non-parametric generalization of information geometry. I don't want to use any explicit parametrization. In some sense, we are forced to use a manifold which is modeled on a special Banach space called Horvitz space. And finally, I don't have in mind actually statistical application. I have in mind application where the problem is intrinsically non-parametric, for example, in statistical physics, or information theory, or optimization, or filtering. In all these problems, you have evolution of densities, but it's somehow impossible to give a parametrization of the evolution. So we want to construct a Banach manifold. So what is a Banach manifold? Given a set and a subset E and the Banach space B, we consider a one-to-one mapping from the subset E to the Banach space B and call it a chart if is one-to-one and the image is open. And this is slightly different than considering what is called a parametrization. A parametrization is something that goes backward, goes from the set of coordinates to the probabilities. And having one chart is not enough actually to construct a geometry. We want an atlas of chart, and so we have to check the compatibility of the charts. If I have two charts, one defined on E sub 1 and the other one defined on E sub 2, they are jointly defined on the intersection of the two domains, and we want to change a coordinate going from the one open set in the Banach space to an open set to the Banach space. An important remark, and we want this change of coordinates to be smooth. An important remark is that in this Banach space setting, the Banach space can be different for any chart. So it's not like in the finite dimensional case where the Banach space is always Rn, but here every chart has a different Banach space. But as the change of coordinate has to be smooth, this Banach space are to be isomorphic. So in our case, the set is a set of positive densities, and we have a chart S sub p for each density p, in such a way that h sub p of p is 0. That is, this is a sort of reference system centered at the density p. And actually, in my construction, the construction is simplified with respect to the general definition, because the domain of the charts, EP1 and EP2, are either equal or disjoint. So actually, in my construction, the manifold splits in non-connected components, and so, in some sense, it's not true it is a manifold on the full set of positive densities. It's actually there are actually different pieces, each piece being quite small. So this is the situation. I put on this picture to remember my notation. We have two reference points, P1 and P2. We have two Banach space, B sub P1 and B sub P2, and we have a chart SP1 and SP2, mapping a generic density Q to U1 or U2, and we have a change of coordinates going to U1 to U2, and we have two domains open domains in the Banach space. So what is E? E is from exponential. E is in some sense the maximal exponential family we can construct around P, around, for example, P1. So first of all, we have to define the model space. The model space is a knowledge space. For example, we take phi of y, hyperbolic cosine minus 1. This is a convex function, 0 at 0, and define the knowledge space associated to phi as a vector space or more random variable such that expected value at p of phi alpha u is finite for some alpha larger than 0. As phi is actually the positive exponential plus the negative exponential, this condition is exactly the condition that the moment generating function of the random variable u is finite in some neighborhood of 0. And or in statistical terms is exactly the same condition that there exists around p a one-dimensional exponential family in the direction u. So in some sense, I've been asked many times why knowledge space, and my answer is that I don't see any other solution. So if you want at least one-dimensional exponential family, the space has to be the only space. There is no other option. So it is possible to prove that this space is this vector space is the Banach space. The unit ball being the set of u where expected value phi of u is smaller or equal 1. And there is a natural way to construct the norm. Precisely, you take u and you divide by rho until you enter the unit ball. This space has a number of issues. Probably the most important one for statistics is the following. A norm of some random variable u is equal 1 if either expected value with respect to v of phi of u is equal 1 or smaller than 1, but divide for something and try to prove that the norm is actually smaller than 1, I can't, because I always get plus infinity. So if phi were the usual square function, the only space would be L2, and this abnormal case would not be there. So this means that the surface of the unit ball is not regular. Well, this construction can be applied in particular to finite state space. In finite state space, everything is simple. All random variable belongs to the correct space. However, the problem is not completely solved because the actual computation of the moment generating function or the phi function is actually computationally quite difficult. Even in the cases that in statistical physics are called solvable, I think, easy models, you can actually do the computation in explicit form, but you find a very from the point of view of computation, something very difficult. It's a big sum of big products. So sum of products is something on which in computer science people has worked a lot, and there are many algorithms to tackle this problem. So what I want to say is that this of course applies to the finite state space, but the finite state space is not as simple as it seems. Well, this is an example to show this problem of the non-regularity of the unit ball. Here you have an example where we take the negative exponential with some factor. This can be computed with the incomplete gamma function, and we get for the phi function as a function of alpha the following result. You have finite result up to -1 plus 1. The value in -1 plus 1 is finite, but after the value of absolute for absolute value of alpha larger than 1, you always get plus infinity. Now I want to talk of something which is very simple actually, but is of key importance. As I want to model my manifold on these spaces, I have to show that at least for density which are not too far, the two spaces are isomorphic. And this is not obvious at all. If you have two different densities, P and Q, L2 of P and L2 of Q are not equal. Unless there is some boundaries condition on P upon Q. So the equality of the L-phi spaces for different Q, which is required by the construction of the Banach manifold, is not obvious in general, but it is true for the Orr space. So we take two densities, P and Q, and consider the closed exponential family, or Ellinger arc, as it is sometimes called, going from P to Q. So it's P to the 1 minus theta, Q to the theta, divided by the normalizing constant you have on the slide. And because of the convexity, this is always finite for theta between 0 and 1. And I ask something more. I ask this to be equal, to be finite on an open interval containing 0, 1. This is the same as requiring that there exists an a one-dimensional exponential family defined on an open set containing in the interior P and Q. So if this condition is satisfied, then the two orange spaces are equal as set, and they have equivalent norms. And I give you the proof because it's very simple and, in my opinion, is important. We have to consider the function integral e to the SU multiplied by the density of the Ellinger arc, d mu. This is a convex function in S and T. And this convex function, if you put theta equals 0, is finite on an open neighborhood of 0 if you assume U to belong to L phi P by definition. And if you put S equals 0, this is finite on an open interval containing 0, 1 but by assumption. Therefore, if you take theta equal 1, so you are in Q, there is an open interval up where this function is finite. So I denote the equivalent condition smile because I like it very much. P is openly connected to Q. So now we can define the chart. So the chart is exactly what we expect to be. We take a reference P, we take the log likelihood, log P upon Q, and we center it. And actually the centering is minus the expected value of log Q upon P, that is plus the divergence PQ. So this is the mapping, and this mapping is defined on a set which is the interior of the proper domain of the function K. So Kp is the logarithm of the moment generating function, the cumulant generating function. This is a complex function. This complex function has a non-empty interior in the space, in the Oli space, and we take the interior of the proper domain, which is an open set, a non-empty open set. And on this set we define the inverse of the mapping SP, EP, that produce backward a density. So this is nothing less than a rephrasing of the theory of the exponential family in